Okay, welcome AP Physics Mechanics students to Differential Equations 2. Just a bit of a warning, this actually will be maybe one of the most lengthy days of notes in the whole year. So it's going to be a lot of details and a lot of solving, so just be prepared for that. Once again, a reminder that these notes are shown in the PDF file that I included in this assignment. So, as I said, this is going to be very lengthy. So once again, it's critical to remember the 4 steps of creating and solving differential equations. Take a second to pause the video and see if in your mind you can list out the 4 steps. Okay, so the 4 steps. The first one is you make a differential equation using Newton's second law. The steps 2 and 3, or step 2, is that you separate the variables. You get all the velocity terms on one side and all the time terms on the other. Step 3 is you integrate both sides. And step 4, you plug in your limits and you solve. Okay? So, first thing, case 2a, there's going to be a case 2b. Okay? But 2a. So something is moving with an original velocity in the forward direction. The forward force is 0. Nothing is pushing it forward. But there's a force of air resistance that's negative kV. This is actually a more accurate model of how air resistance really works. It's not like the friction when you drag one object over another. That's always a constant mu F normal. The force of air resistance actually varies and gets greater the faster you go. So imagine you're driving your car in a parking lot going 5 miles an hour. You put the window down and you stick your hand out the window. You'll feel a very slight air drag pushing your hand backwards. If you get going 50 miles an hour with the window open and you stick your hand out the window, you're going to feel more force in the backward direction. Go 100, and now your hand's really being pushed back. So the faster you go, the more air resistance you have. That's why we have kV. K is a constant that depends on how aerodynamic the object is. The bigger K is, the more air resistance we have for a given velocity. So a big K might be for like a big pickup truck. And a smaller K would be like a Lamborghini that's shaped like a bullet that can cut through the air. So it's to factor in the shape or the aerodynamic properties of the object. Now, I'm launching this forward and it's coasting to a stop with air resistance. I just want to remind you that we got gravity, normal force, balancing, and only a backwards air resistance. There is no forward force. A lot of students, when something slows down, they want to put a forward force and they say, well, what's keeping the object going? This would just make it go backwards. Remember, Newton's first law, objects stay in motion with 0 force acting on them. If we remove this, this object just coasts forever in the forward direction with 0 force. The backwards force is to slow it down, okay, and decelerate it. All right, so that's the situation. So to find out the velocity as a function of time, we follow our process. Step 1, we make a differential equation using Newton's second law. A equals F net over m, but A is actually the derivative of velocity with respect to time. F net is the backwards minus kV over the mass. That's the net force over the mass. So how do we separate the variables? What we can do is move the dt to this side and divide the v to this side. So we have all the velocity terms on one side and all the time terms on the other. So now I integrate both sides now that I have the equation, the variables separated. Remember, I'm starting at some velocity and I'm slowing down. So I start here and I'm looking for this final velocity that I slow down to. And the timer begins at 0 and goes to some final time. So dv over v just integrates to the natural log. And then dt just integrates to t, and then we have the constants there. And then we apply our, evaluate for our limits. And then the fourth step is we plug in our limits and we solve. So let me move this up. So here we are. And then we plug in v final into the log and v0 into the log and t and 0 into our function there. Now, two logs, when you subtract them, they can combine into one log as long as you put the arguments inside as a quotient. So we have vf over v0 inside, and this side just negative kt over m. We got to get rid of the natural log. The way we do that is we plug in both sides of the equation into the exponential function. E to the log gets rid of the log, and we're just left with v final over v0. And then this is e to that, e to the negative kt over m. And so what we have is our final velocity, when we move that to the other side, is the original velocity times the exponential negative to the negative power. Remember in the previous video, e to the negative variable starts at 1 and decays down to 0. So this is v0 times 1 and goes to v0 times 0. So it starts at v0 and gradually falls to 0, which is what we'd expect from our situation that I described earlier. Okay, so now we want to know how far this thing went. In other words, its x-coordinate. So we realize that this is actually yet another differential equation. So we follow our 4 steps again. Can you remember what they are? Okay, you might want to pause the video and see if you can say them in your mind. So we make v into dx dt. That's step 1. We made the differential equation. Step 2, we separate the variables. I move the time, the dt, to this side because time is on that side, leaving only x by itself. And there's nothing with respect to x over here, and there's nothing with respect to time there. So I separated the variables. That's step 2. Step 3 is now I integrate both sides. I started at 0, and then I go to some x final. The timer started at 0 to t final. dx integrates to x, the simplest of all integrals, evaluated over our limit. And then the exponential, if you remember from the previous video, it integrates to just the exponential. And we would be done if it were e to the t power, but it's not. It's e to a function. So what we have to do is divide by the derivative of what's inside. The derivative of what's inside is negative k over m. We divide by that, which is the same as multiplying by the reciprocal minus m over k. And now we have to plug in our limits. That's the 4th and final step, and solve for x. So we'll do that over here. Okay, so there we are, x final minus 0, and then we plug in t final into the exponential and 0 into the exponential. Now recall that e to the 0 is 1, so we have e minus 1. And then I'm going to distribute this minus sign to make that negative 1 actually positive 1 and make the exponential actually negative. So what I have is the 1 minus exponential. Recall from the previous video, that's a function that begins at 0 and then rises to 1. So I have 0 times this in the beginning, which is 0, and then 1 times this. So the object eventually goes to a distance of mv0 over k. So that's how far the thing went. And then often what we want to do is we want to find the acceleration as a function of time, not as a function of velocity as it was earlier. If you look back in the notes that are not on the camera right now, not in the camera's view, you will see that acceleration was a function of velocity. The way to get it as a function of time is you use the idea that acceleration is the derivative of velocity with respect to time. So then you plug in your velocity function, which we solved for earlier, v0 times exponential negative, and you take the derivative of that. The derivative of the exponential is just the exponential, but we have to fix that up because we have to use the chain rule, and we have to multiply by what the derivative of what's inside, and the derivative of what's inside is negative k over m. So we multiply by negative k over m. And then basically we just kind of touch that up to minus kv0 over m times the exponential to the negative power. Interpreting this, we see that the original acceleration, it starts at 1 times this. And you could see F over m here. kv0 is the original air resistance over the mass. So there's the original F over m, and it exponentially decays to 0. So there is our acceleration as a function of time. Very often, we graph these functions. So that's the next thing that we do. Okay. And there, I guess that's on the screen now. So remember the x function was the 1 minus exponential. So it starts at 0 and rises to some constant value, the term that's in front of the 1 minus exponential. The velocity was a simple exponential decay that started at v0. And then, so that's that. And then the acceleration, which we have right up here, is an exponential decay from negative k v0 over m. So there's the original acceleration. It decays to 0. So that was a lot. Remember, that's only case 2a. An object projected forward with no forward force, stopping because of a backwards air resistance force. We now have to look at case 2b. So people, we are only halfway there. As I said, a warning, this is going to be a long note day, one of the longest of the year. But I'm confident we can all get through it. So, case 2b is the same mass, now beginning at rest, stopped. And then there's the constant forward force and the backwards air resistance force that gets bigger the faster you go. So here's what's happening. We're pulling this forward with a constant force. We have gravity and normal force balancing. That's the earth pulling down and the surface supporting. Okay, the forward force and then the backwards force of air resistance. Now, what is this in real life? In real life, this could be like a car, any car. You're not moving, and you floor the gas pedal. And let's suppose the car has a very special engine that has a constant forward force. No car has this. They all have transmissions that shift gears, and you can feel the lurching. That's the shifting gears, the variable forward force. But we're going to simplify it and imagine we have a very special car that just pushes forward at a constant amount. What happens is the faster you go, the more air resistance builds up, as I mentioned earlier in the video. And so whatever car it is, no matter what car it is, you go faster and faster until this backwards force exactly matches the forward engine force. And that doesn't mean the car stops. It means it stops accelerating. The net force will be 0. We'll have 10,000 newtons forward, 10,000 newtons backwards. Whatever the engine forces will be matched by air resistance, and then the thing will go at a constant velocity. It will no longer accelerate. We have reached the top speed of the car. So maybe for a Lamborghini, that's 150 miles an hour. I don't know what a top speed of the Lamborghini is, but it's fast, right? Maybe a Honda Civic, the top speed's 110. Regardless of what the car is, eventually, no matter how powerful the engine is, it makes the car go fast enough until these two forces balance. And then the car has reached its top speed. That's what we're going to be analyzing. That's what we should see in our solutions. A velocity that begins to 0 and then reaches its top speed, whatever that may be. So again, can you remember the 4 steps to solving a differential equation? Pause the video and see if you can say them to yourself in your mind. Absolutely critical that you can do that. So, here they are. Step 1, we make a differential equation using Newton's second law. A equals F net over m. We realize that A is actually a derivative of velocity. And then we have the forward force minus the backwards force for net force over the mass. Step 2, we separate the variables. That means we put all the velocity terms on one side, all the time terms on the other. Okay? But here's the thing, a very common mistake students will make is they will split this up into two fractions, f over m and minus kv over m, and add this term to the other side. And the problem with that is that you'll eventually have dv plus velocity, which doesn't integrate. So you never separate the variables by adding or subtracting. You always divide or multiply. And so what we do is we take this entire numerator and we divide it to this side. And we move the dt to this side. So when we move this numerator away, we have 1 over m, and then the dt joins it on that side. And then on this side, we've got dv divided by that entire numerator there, f minus kv. We've separated the variables, all velocity, all time. Now, we integrate both sides. Remember, the car began at rest and I floored it. I pressed the gas pedal all the way down, and I'm going to find the final velocity. The timer began at 0 at the beginning of my experiment, and it's going to go to some final time. So those are the limits. So, over here I have dv over v, which integrates generally to the natural log of that entire denominator. But this negative k in front of velocity generates this 1 divided by negative k. You can figure that out using a u substitution, which I did not do because, as you no doubt feel, these notes are long enough. So I didn't do that. You could simply, when you solve this, memorize that when you integrate, you get log of that entire term in the denominator, then you have to divide by that negative k, okay, over the limit 0 to v final. This side integrates trivially dt to t from 0 to t final. The fourth step after we integrate is now to plug in the limits and solve. So that's what we're going to do next. Okay, so let's see, how high do I have to go? Right around there. Okay, so I plug in v final first into this term, log of f minus kv final. Here's a common mistake, another common mistake. Students say, oh, 0. I plug that in, so it's this minus 0. Okay, because I plug in 0. No, you're plugging in 0 for the velocity, not for the entire function. So we plug in 0. That gives us log of f minus 0, which is f. And again, actually I didn't mention it, but the minus k I moved over here. So that's why it's not here. It's been moved to the other side. Okay. And then I plug in my limits t final and 0. Now again, as before, we can combine the logs into 1 with division, and this side just simplifies to that. How do we get rid of a natural log? We put it into the exponential function, both sides. That eliminates the log, but makes this side e to the minus kt over m. And then I move the f to the other side, and then I just do a little algebra. I added the kv to this side, I subtracted this to this side, I factored out an f and divided by k, and I have my final velocity. Okay. Notice again that 1 minus exponential. That means the car starts at 0 velocity, 1 minus exponential, and then it rises to, this parenthesis term rises to 1. Okay? So I have 1 times f over k. So the velocity starts at 0, rises to f over k. An interesting thing, notice the mass of the car is not in the answer. Okay, the final velocity, f over k. Take a Lamborghini, according to this theory, this analysis, fill it with cement, and it will not affect its top speed. All it will do is make it take a longer time to get to the top speed. But the top speed will be the same no matter what the mass is. It only depends on the force of the engine and the aerodynamics of the car. The smaller k is, in other words, the more aerodynamic, the faster the car can get going in the end. Alright, so that's our velocity function. Take a deep breath, because now we have to go 2 more things. How far does this car go, the x? We solve this again by going through the 4 steps. We take this velocity and we turn it to a differential equation by substituting dx dt. So we defined a derivative. And for the sake of simplicity, what I did is I distributed this and broke up the parentheses. It'll make it simpler to integrate later. Step 1, made a differential equation. Step 2, separate the variables. So what I do is, let's see, right around there should be good. Okay. Yeah. So I move the dt to the other side with all these terms, and that's all I had to do to separate the variables. I have all time on this side, all x's on this side. Dx integrates trivially, and then I integrate both sides. Dx trivially integrates to x from 0 to x final. These are constants, so this times dt integrates to the constants times time. And then the exponential dt, notice the f over k is here, they're just constants, but the exponential integrates to just the exponential. But again, what I have to do is divide by the derivative of what's inside. What's inside, the derivative is negative k over m. And then I divide by that, which becomes minus m over k over the limits. So then, basically now the fourth and final step is I have to plug in the limits and solve for the answer of x minus 0, okay? And then on this side, I plug in t final and 0 in for that time, so that's that. And then these terms all combine to there, and then I plug in t final into the exponential and 0 into the exponential. And the rest is just touching it up, so you could look at that in more detail later. Okay, the next thing that I want to do is solve for the acceleration as a function of time, not as a function of x. And I can do that by just using the basic idea that acceleration is the derivative of velocity with respect to time. d dt of our velocity function, which is over on the lower side here. I covered it up already. It's off the screen. So the derivative of this is 0 because it's a constant. The derivative of the exponential is just the exponential. And we have these f over k, another mistake maybe? Yes, f over k right here. Okay. All right. Okay, so there we are. F over k, and then so that's here, right? And then the derivative of the exponential is just the exponential, but then I need to multiply by the derivative of what's inside, which is negative k over m, right there, okay? And then basically I touch everything up, and there it is. Notice I have f over m, the original acceleration, when there's no air resistance because the car isn't moving yet. And that exponentially decays to 0. Okay? The last thing, graphs. So the function for x, which is pretty complicated, it would basically be like this. It would be start off similar to a parabola. That's what all this does. But then eventually it goes linear. Like this term, e to the negative, it basically goes to 0. So then we have basically this, a linear function, t to the 1 power. That's the car when it reaches its terminal speed because it's going so fast. The velocity was the 1 minus exponential function, which we saw earlier, and it rises to f over k. And the acceleration decays starting at f over m and decays to 0. There it is. A very long lesson, right? So hopefully you survived, and great job for following along. Again, I just want to point out, look at all the details. If you look at your notes, it probably looks pretty crazy. All the symbols and all this. Remember those 4 steps. Create a differential equation with Newton's laws. Okay. Separate the variables, get all velocity on one time, all velocity on one side, time on the other. Integrate both sides, and then solve for the velocity or x. Okay, if you can remember those, it becomes easier. Okay, so that's differential equations part 2. Okay, so I'll see you in the next video where we do differential equations 3, which mercifully is going to be shorter.